Hello, my name is Jeffrey Bindeman. This is my introduction to R final project. My data comes from the mobile game Fate Grand Order. I retrieved the data from a website called the Atlas Academy, which is a database that is automatically updated with the most recent live version of the game. They also have an API for serving that data at the pictured link. The API returned JSON data that I was then able to read with Python. I then trimmed it down to only include the few details that I'd be performing analysis on and wrote that to an Excel file. That data contains 329 rows with 19 columns, two of which, collection number and name, were used for indexing and identifying the rows. Before getting into what any of that data means, let's first analyze what it's about. Fate Grand Order is a type of mobile game called a gacha game. The name comes from the gachapon machine, pictured on the right. You might have seen them around before. They're a machine that you insert a quarter into and turn a knob, and you might receive a small toy or a candy or a random tattoo. Similarly, in Fate, players use in-game currency to try and obtain random in-game items in a process called rolling. This is a system also referred to in other games as loot boxes. While there are all sorts of things that can be obtained from rolling, the only ones I'm concerned with for this project are the playable characters, who in the game are referred to as servants. As previously mentioned, there are 329 different servants, each with 19 columns. Collection numbers and numerical ID assigned to each servant. They are assigned in the order that the servant was added to the game, so can also be used as a scuffed way to gauge time. Name is, of course, the servant's name. Rarity is how likely a character will appear while rolling. Higher rarity characters tend to have better stats than lower rarity characters, as we will see. Gender is, of course, what the servant's gender is. There are three genders, male, female, and a special unknown used for characters that don't quite fit into either. As an example, one of the servants is Enkidu, from the Epic of Gilgamesh. He was a clay doll fashioned by the Mesopotamian gods to fight Gilgamesh, and because he's made of clay and neither male nor female, he has a gender of unknown. Attribute is a trait that every servant has that increases or decreases damage dealt to servants of a different attribute. They also indicate where a servant's real-world counterpart comes from. Building off the previous example, Enkidu, as someone created by the gods, has a sky attribute, whereas Beowulf, a character from myth, has the earth attribute. Strength, endurance, agility, magic, luck, and NP are all stats that add a little bit of lore to the characters, but they don't actually have any in-game effects. However, I thought it might still be interesting to analyze, so I included them. In Fate, battles are turn-based, meaning your characters take a turn dealing damage, and then the enemies take a turn, and then your characters, and so on and so on. The card count attribute indicates how many quick art or buster attacks a servant has. They all have at least one of each, but the other two can be any other type. So a servant might have 2 quick, 2 art, and 1 buster, or 1 quick, 1 art, and 3 buster, but they must have at least one of each, hence the range 1 to 3. Next are crit stars. When an enemy is hit, they will drop items called critical stars. These stars go into a pool that on the next turn is distributed to the characters you control. How many stars an enemy will drop is tied to the attacking servant's star gen value, while how the stars are distributed on the next turn is tied to each participating star absorb. Basically, characters with high star gen will create lots of stars, while characters with high star absorb will take them. Finally, there's attack max and HP max. Attack max is just the highest value a servant's attack stat will go, while the HP max is the highest amount a servant's health will go. Rarity and these last 7 attributes are the only continuous variables. The rest of the data set are all categorical. Now here are the summary statistics for those continuous variables. We can see that the mean rarity is just over 4. Art cards seem to be the most common as they have the highest mean among cards, while quick cards are the least common as they have a median of just 1. The average max attack is just over 9,500, while the average max HP is just under 12,000. Now for the graphs. In this graph, we can see all the different rarities of servants grouped by what class they are. Interestingly, the most plentiful characters are 4 and 5 star characters, the least common being 1, 2, and 3 stars. At first, this might not make a lot of sense, as you'd think that the most common characters should be the least rare. However, rarity is also related to how high a character's stats are, and few people would want to use characters that aren't good. In this graph, we see all the star absorb values, again grouped by servant class. You can see several overlapping groups. This means that if you have those types of servants together on a team, they'll be competing for who gets the stars. However, if a servant of a higher group were on the team, they would likely take all the crit stars instead. The 2 things I find most interesting are berserkers and riders. I've known for a long time that berserkers tend to have a really low star absorb value compared to the other classes, but I didn't realize it was this low. I also didn't realize that riders have such a higher value than the other classes. One of the things I was wondering about the data is what the traits of servants post-launch look like. For example, perhaps there might have been a tendency to create more sky attribute servants. After all, sky servants tend to be related to gods, and they're all extremely powerful. And based off that first graph, we saw that developers like to add strong servants rather than weak ones. So I took a subset of the data, removing those first 59 servants that were risen in the game, and charted the cumulative sum of each trait and gender across collection number, which again, as previously mentioned, can be used as a metric for time. It is interesting to see that the distribution of attributes is actually pretty linear. Also interesting is how the number of male and female servants remains steady up to a point before the number of female servants just shoots through the roof. Losangle, the company that makes the game, certainly knows their male demographic. This graph compares the maximum attack displayed in red and the maximum health displayed in blue, 5 and 4-star characters respectively. Interestingly, if we look at where the data is grouped here, we can kind of see on average, that 5-star characters have greater attack than the average 4-star characters. But also interesting is if we look at health, it does seem that the average 4-star character has a higher health value than average 5-star characters. Here we see 6 radar charts for the average lore stats, again grouped by servant rarity. As previously mentioned, the lore stats don't have any actual effect on gameplay, but I thought it'd still be interesting to see how they stack up together. Unsurprisingly, there are very little difference in the high tiers, with 5-star servants only having a slightly better average than 4 and 3 stars. Meanwhile, 2 and 1-star servants have the worst lows. Meanwhile, 2 and 1-star servants tend to have the worst lore stats. There's actually also a secret 0-star servant named Angamainu. He's the only 0-star, so I thought it'd be interesting to see what his lore stats look compared to everybody else. Again, unsurprisingly, his stats are by far the worst out of everybody, but as a special guy, he also has the highest agility trait of anybody, which is kind of neat. This last graph shows how card counts might affect star gen. Truthfully, these are the last remaining variables. I didn't really know how else to use them. But that being said, I think there's still some interesting information that can be gleaned here. For example, for most servants, Buster card count has nothing to do with star gen. However, there are a select few that have a really high star gen if they only have one Buster card. This last graph shows how card counts might affect star gen. Truthfully, these are the last remaining variables. I didn't really know how else to use them. But that being said, I think there's still some interesting information that can be gleaned here. For example, for most servants, Buster card count has nothing to do with star gen. However, there are a select few that have a really high star gen if they only have one Buster card. And I think this is due to there being a lot of servants with 3 quick cards that have also really high star gen. And this makes sense, as the whole point of quick cards is to make crit stars. So servants with a high number of those cards should also have a high star gen value to match. Now let's talk about linear models. Based off this correlation matrix, we can see that the variables with the highest correlations are rarity and attack max, rarity and HP max, attack max and HP max, star gen and quick card count. Art card count and Buster card count also look moderately negatively correlated, so we'll take a look at that too. First is rarity against HP max and rarity against HP max. The former is on the left with the latter on the right. In both models, we can see that the data is pretty normally distributed. Due to the scale, they also both look basically centered at 0. As for the R-squared values, both are pretty high, but I still don't think that the models fit the data very well. This is due to many of the data points either being over or under predicted, and sometimes by quite a wide margin. There's a trend that we will see in this data. Next is HP max against attack max. The data is still pretty normally distributed. The median is negative 33.2, but again, due to the scale, it's basically centered on 0. These R-squared values are pretty high, and I think this is an okay fit. However, there's still some significant over and under predicting, and again, sometimes by a lot. The major contributing factor here, I think, is going to be rarity. I feel pretty confident in saying that all these big groups here are related to how rare a character is. So like this first group is 5-star, the second group is 4-star, maybe here are the 3 stars, and then here is like the 2 and 1 stars. So if the data points were further separated by rarity, I think the resulting linear models would actually be much more accurate. The next model is quick card count against star gen. Unlike the others, this data is definitely skewed towards higher values, but it is at least still centered at 0. However, these R values are absolutely atrocious. This is because quick card count is not at all related to star gen. If you'll recall, attacking enemies drops critical stars. The higher the star gen of the attacker, the more critical stars will be made. Additionally, the quick attacks are the ones that will drop the most stars. And as such, characters with lots of quick attacks would inherently want to have a high star gen value to make the most of their attacks. It does not mean that they are actually correlated. The final model is art card count against Buster card count. Unlike all the other data, this data is highly centered on 0. It is also pretty skewed towards negative values. However, similar to that last graph, it has horrendous R-squared values. This is because both the variables are also factors. So while it looks like there's only 6 points, in actuality, all 329 servants are represented in the data here, stacked one on top of the other. This makes this model an extremely poor fit. I don't think these variables are actually correlated at all. Anyways, that was my presentation. Thank you for watching.